Hey, hi. If you create a linear regression model using the Stats Model API and not the sklearn package, then you will get a detailed report about a lot of different statistical properties that are used to create the linear regression model, which can be useful to infer if a feature is relevant to a target variable or not. In this video, I aim to go over that Stats Model API report in detail so that there is complete clarity in terms of how linear regression model works. I hope you all like the video.
Before we start the video, I have one simple assumption that you already know what linear regression is, what is the target variable in case of linear regression, what is multicollinearity, and the other fine details of how linear regression is. The one thing that a lot of data scientists or machine learning engineers fail to understand is the statistical significance of linear regression, the p-value associated with a variable, the overall f statistic, the r squared value, and so on and so forth. So in this video, I'll walk over a simple stats model report to make you understand if my linear regression model that is generated is a good fit model or not. So let's start by importing the necessary modules. I have a simple CSV file called as data.csv which I load into a data frame df. The data frame has a total of 200 rows and 4 columns. Let's also see the first 5 rows of the data frame. So as you can clearly see, there are three features, all of them are numeric in nature, and I have a target variable which is continuous in nature, that is it's a regression problem. So three features and one target variable is all that we have right now in our data set. Let's proceed ahead. I create a simple variable called as target underscore call, which is equated to the word target, and this is used to separate out my x and y values, where x are my feature variable values and y is my target variable value. So for this tutorial, I'm skipping the whole EDA exercise, which is an integral part of model building, just because I want to focus on one part of linear regression, which is understanding the various tests which are there in linear regression, the values, what is their significance, and so on and so forth. So now if you go on and directly create a model using scikit-learn, then the first step is to create an instance of linear regression, fit your x and y values, and extract out the coefficient and the intercept. Since I have three features, feature 1 has a coefficient of 0.04, feature 2 has a coefficient of 0.18, feature 3 has a coefficient of negative 0.001, and there is also an intercept value of 2.938. Most of the data scientists would stop here assuming that it's a good fit model by checking the r squared value and so on and so forth. But there is a lot in linear regression that a lot of people miss out. So directly using the scikit-learn package is not something that is advisable. I would highly recommend people use the stats model API to create linear regression models, as it gives a comprehensive report of how good a fit your linear regression model is. So the way you do that is you call the add underscore constant function from the stats model API, which is imported as SM, and add a constant column. So you will have a column with just ones and append it to the actual X column. Fit your OLS model with values Y and X and save those results into a variable called as model. So I run this cell. In the previous step, the model understood what Y values are and X values were, but it's not actually fitted the whole variables and computed the coefficients and the intercepts. So you have to call the function called as dot fit. So I call this function, and this is what I get in terms of the coefficients of constants and features. So if I go up, my constant value is 2.938889, which is something similar to what I'm getting using the scikit-learn package. Feature 1 has a coefficient value of 0.045, which is the same as what I'm getting here. So the results are in parallel with each other, so there's no difference in the results if we use either scikit-learn or the stats model API package. But the place where OLS model takes an advantage is the summary report that it generates. It gives you a comprehensive report of how the model is fit, what are the parameters that you should look at, what are the different tests that are performed to validate if a feature is necessary or not. All of that is covered in this regression result report. So I start off by something called as the R squared value and the adjusted R squared value. I won't go into the whole calculation bit because there are a lot of videos out there that cover the calculation of how R squared is captured and how adjusted R squared is captured. My whole idea is to give you an understanding based on the report if your model is good fit or not. So in statistics, the coefficient of determination, that is denoted by R squared, is the proportion of variance in the dependent variable that is predictable from the independent variable. A lot of tutorials out there that can explain what these terms mean, but the whole idea that you have to keep in mind is if your linear regression model is fit really well, then you will have an R squared value closer to 1. There is also a misconception that R squared value cannot be negative. In case if you fail to follow the best practices for linear regression, there are chances that you might not even get a positive R squared value. You would even land up with an R squared value of minus 190, minus 63 and so on and so forth. A value closer to 1 is what something that you would expect if your model is really fit well. However, there is a simple thing that you also have to remember. You have something called as R squared and adjusted R squared. If you keep adding features in your overall model for a better prediction accuracy, then there are chances that your R squared will remain at a higher value closer to 1. However, adjusted R squared accounts for this by penalizing R squared values that include non-useful predictors. So if you go on adding features which are of very little relevance to your overall model, adjusted R squared value would go down. If your adjusted R squared is much less than R squared value, it's a sign that a variable might not be relevant to your overall model. You just have to find that variable and omit it. In our case, my R squared value is 0.897 and my adjusted R squared value is 0.896. So it's a very well fitted model wherein I don't have any feature that is blowing my overall model performance out of proportion. So that is the reason you first have to visualize the R squared value, how close it is to a value 1. Secondly, you also have to understand if your adjusted R squared and your overall R squared are poles apart. If they are close enough, then you have selected relevant features. If they are really far apart, then there are chances that you've included a feature which is less relevant. So this is what I had to cover in terms of R squared and adjusted R squared. If this idea is clear to you, let's go on to the next variable that is there, which is called as the F statistic. F statistic or the F test is used for assessing the significance of the overall regression model. In multiple regression, which is the case wherein you have multiple features, which is the case that we are dealing right now with, it compares a model with no predictors. That is, in our case, there wouldn't be feature 1, feature 2, feature 3, which is also referred to as intercept only model. So you'll have only an intercept value, which is in our case 2.9389, to the specified model that we have, that is with feature 1, feature 2, feature 3. The null hypothesis in the case of F statistic is that these two models are equal. And the alternate hypothesis is that intercept only model is worse than our model. We will get back a p-value as well as a statistic value that will help you choose whether to reject or accept the null hypothesis. Given this p-value is close to 0 and the F statistic value is really large, we can reject the null hypothesis. In plain English, there is an evidence that there is a linear relationship between feature 1, feature 2 and the other set of features, that is feature 3, and my target variable, which is denoted by my overall F statistic and the p-value of the F statistic. An F statistic greater than 1 or a really large value of F statistic plus a p-value, that is your probability of F statistic value, less than 0.05 signifies that there is a good amount of linear relationship between my target variable and my feature variables. Okay, so this is the whole test. The derivation, the formula and all is something that you can find in a lot of textbooks, so I'm not going into the details. I'm helping you understand the overall result that you're deriving from the OLS model summary. If this part of the whole result is clear, coming to these features which kind of help you understand even better if there is any multi-collinear features, which features are actually relevant to your model, can you drop one of the features after creating a linear regression model and so on and so forth. All of these assumptions or all of the hypotheses that you have in mind can be sorted out from this part of the table. In order to infer if a given feature is significant or relevant to the target variable, we perform a t-test. Now the t-test behaves slightly differently from the f-test. It looks at a relationship between the target variable and every predictor variable independently without taking into account all the features at once. It goes one feature at a time. So you will have a t-test performed between feature 1 and my target column, feature 2 and target column, and so on and so forth. The null hypothesis of a particular feature is that the feature 1 value is going to be equal to 0. And the alternate hypothesis is that the feature coefficient value will not be equal to 0. And given this hypothesis that I have, I perform a t-test. So you have t values and you have a given p value associated with that t-test. Higher the t value, the greater the chances that you reject the null hypothesis and you accept the alternate hypothesis. Lower the value of p, that simply signifies that you again reject the null hypothesis and you accept the alternate hypothesis. So in our case, if you look at just the p value columns, so for the constant variable, that is 2.9389, so you have a p value of 0.000. Similarly for feature 1, you have a value of 0.00. Feature 2, you have a value of 0.000. So essentially all the three terms have a p value less than 0.05 because you're testing the test at 95% confidence interval. So you reject the null hypothesis and you accept the alternate hypothesis, stating that the weight values of these particular features are non-zero. Whereas if you look closely at feature 3, the coefficient is negative, which is still okay, but the t value is very small. On top of that, the p value is very high. It has a p value of 0.860. So if you again go by the understanding of what p value is, if your p value is less than 0.05, you reject the null hypothesis and you accept the alternate hypothesis. If your p value is greater than 0.05, you fail to reject the null hypothesis. So in our case, we fail to reject the null hypothesis, which is the coefficient of feature 3 is having a value 0. So essentially this feature that I have, that is feature 3, is irrelevant in case of our linear regression model, and we can also drop it and not use it later on to make a prediction. So this was my take on how you can interpret the overall stats report that is generated, which gives you a clear picture of how you can interpret your overall linear regression model. If you do have any questions with what we've covered in this video, then feel free to ask in the comment section below and I'll do my best to answer those. If you enjoy these tutorials and would like to support them, then the easiest way is to simply like the video and give it a thumbs up. And also it's a huge help to share these videos with anyone whom you think would find them useful. Please consider clicking the subscribe button to be notified for future videos. And thank you so much for watching the video.